The final module in Chapter 21, Module 4, looks at derivative prices as discounted cash flows. In Chapter 10, we developed an equation based on our binomial lattice that said that the call option, or an option price, is the present value of an expected payoff. This came, and P star was our risk-neutral probability, and we have the risk-free rate. Another way of writing this, and we've seen this before, is that the derivative value at time t is the expected value, using risk-neutral probabilities, of the present value, using the risk-free rate, of the future values. In other words, it says that today's price is nothing more than the present value of an expected future price. The present value uses the risk-free rate, and the expected value uses the risk-neutral probabilities. We saw this generalized to a multi-period binomial lattice in Module 10, or Chapter 10, Module 5, and we saw that if we have a European option on a binomial lattice with n steps to expiry, we can calculate the price of that option directly in terms of the expiration values of the option, the exercise values, by doing a single step calculation that goes from the exercise value of the option at time t, and then doing a expectation using binomial probabilities and the risk neutral p, and using a total period discount factor with risk-free rate of r. And so here we broke up the time period from little t to capital T into n steps of size h each. And it's natural to wonder whether this idea that today's price is an expected present value of exercise prices, is this also consistent with the Black-Scholes continuous model? Is it also the case that the Black-Scholes prices can be thought of as a present value of an expected payoff where the expectations use risk-neutral probabilities? We've seen it with the binomial lattice in two-step, three-step, multi-step. It's logical to expect, since we have been told, although we do not prove it in these sessions, that the price with the binomial lattice converges to the Black-Scholes price. This is what Cox, Ross, and Rubinstein proved in their paper. But the binomial prices will converge to Black-Scholes, and since the binomial prices are defined by expected present values, it's natural to think Black-Scholes should also be an expected present value. Turns out it is. The notation here is a little bit messy, but what the Black-Scholes analysis basically says is that every derivative price is a present value of an expected payoff. C of S of t, think of as the expiry values. It's the exercise value of the derivative C at time t when the stock price is S of t. And what this is this is the probability distribution under the risk-neutral measure of stock prices. So the idea is the same as we saw in the binomial lattice, namely that today's price for any derivative is the present value of an expected exercise. And when we calculate the expected, we need a probability distribution that reflects the risk-neutral measure. Now, obviously, under the Black-Scholes formula, because the distribution of stock prices is continuous, instead of having a discrete summation, as we did with the lattice, we have an integral that calculates the expected exercise value of the option, and that's what this is. This is the exercise value of the option, and this is, we're calculating the exercise, the probability distribution. And in fact, we know that probability distribution from earlier work. We know that the stock price at expiration is the initial stock price with a normal return. Stock prices are log normally distributed. So in fact, we have an explicit expression for the probability distribution of stock prices, namely that the stock price at expiration is the initial stock price times e to a normal random variable, and xt has this normal distribution we've seen time and time again. It has a mean of r minus delta minus the half sigma squared, all times t, and it has a, or t minus t to reflect the interval of time, and it has a variance of sigma squared times the interval of time. And so we can actually write down this is the probability distribution for a normal random variable x that has the given mean and the given variance.